Hi, this lesson is about resistance and it's the fifth lesson in our electricity topic. Now, before we move on, let's have a quick recap of the two major concepts we've learnt about so far. So, pause the video and try and fill in these sentences. So you should know that current is the rate of flow of electrons or charge. Both terms could be used interchangeably. And voltage, you should remember, has two meanings. It can be defined in terms of force or in terms of energy. First of all, in terms of force, it's the force pushing electrons through a circuit. And in terms of energy, it's the electrical energy transferred in a circuit. Based on these two definitions, voltage is also known as electromotive force, and it's also known as potential difference, the two different definitions it has. So the first major concept we learned about was current, the second voltage, and the third major concept in this topic is resistance. So, where do we see resistance in the wider world? And what actually is resistance? Here we have three situations. The first is a man running on the road. It's actually from Forrest Gump. The second is some people running on what looks like a very muddy surface. And thirdly, we have a person running underwater. Of these three situations, which do you think has the highest resistance? And which do you think has the lowest resistance? So, this right here has the lowest resistance because it's relatively easy to run on the road. And this would have the highest resistance because you would find it extremely difficult to run underwater. So, simply put, resistance opposes motion. And what we see is, as resistance increases, the energy required or the force required to overcome that resistance also increases. So for example, this person here will be using a lot of energy and exerting a lot of force to overcome the resistance of the water. And this person here would be using relatively less force and less energy because he is facing less resistance. We also see that motion and flow decreases. So we can see that this person is moving considerably slower and he's moving much faster over here. So motion and flow decreases when we have higher resistance. Let's see how this plays out in electricity and electrical circuits. So here we have a circuit. We have a battery with a voltage of 9 volts. We have a resistor with a resistance of 10 ohms in this case. And we have an ammeter to measure the current. Now when I close the switch, look at these values and try and identify the relationship between voltage, current, and resistance. Voltage, current, and resistance. Try and figure out the relationship. Okay, let's try another example. So, in this case, our voltage reading is now 5 volts and our resistance is 2.5. Try and predict what our current value will be. Did you get it right? And can you see the relationship between voltage, resistance, and current? It should start making a bit of sense now. Let's try one more. Here we have one more example. What do you think the current value is going to be? Let's close the switch and find out. It's 1 amp. Hopefully you can now see the relationship. Let's now look at this on a more mathematical basis. So, as we saw, resistance is the opposition to the flow of charge, or the flow of electrons. Essentially, it's anything in a circuit that reduces the current flow. We also saw that voltage, current, and resistance are related by this equation. What this means is, if you want to push a lot of electrons through a circuit very quickly, essentially if you want to have a high current, you're going to need a large force and have a lot of energy, meaning you're going to need a large voltage. Also, if you have a very high resistance that opposes this current flow, to overcome that resistance, you're going to need a large force. You're going to need a lot of energy, which means you're going to have a high voltage. And finally, if you have a large resistance in the circuit, you're going to stop a lot of current flowing. You're resisting that motion, you're resisting that flow. So high resistance means low current. Voltage is given by V. Current, as we know, is given by I. And resistance is given by R. So it's very common to hear this equation as V equals IR. Voltage is measured in volts. Current is measured in amps. And resistance is measured in ohms. And you should know that this symbol here is the symbol omega. Let's try a question. A voltmeter reads 8 volts on a filament lamp. If the resistance of the lamp is 6 ohms, what is the current that will flow through it? Pause the video and have a go. So, the first thing you should do is write the equation. Voltage equals current times resistance. Then we're going to substitute our values in. So we know that resistance is 6 ohms, voltage is 8 volts, and we need to calculate current. So our voltage value is 8.0 volts. Our current value is unknown, so we're going to leave that as I. And our resistance value is 6 ohms. At this point, we need to rearrange the equation, or we need to just divide by 6 on both sides. So we'll get 8 divided by 6. Current is equal to 1.3 amps. And that's it. Let's try one more. Read the question, pause the video, and have a go. So, in this question, an ammeter reads 1.5 amps on a filament lamp. If the resistance of the lamp is 25 milliohms, what is the potential difference of the lamp? So here we need to calculate potential difference. And remember, potential difference is the same as voltage. So our first step is to write our equation. V equals I times R. Remember, voltage equals current times resistance. Our voltage value is unknown, so we'll leave that as V. Our current value is 1.5 amps, and our resistance value is 25 milliohms. Now the trick in this question is to note that it's 25 milliohms. So we need to convert it from milliohms to ohms. So 1.5 amps remains, and milliohms is 25 times 10 to the minus 3. That's what the milli sign means. And we can simply put that into our calculator and we'll find a value for voltage. And now we know that voltage is equal to 0.0375 volts. Now we're going to investigate the relationship between voltage, current, and resistance. Pause the video and draw this table out first. Here we have a circuit. We have a battery, an ammeter, and a resistor. Now our resistor is 2.5 ohms. That's its resistance. And our battery is currently at 0 volts. That means it's not pushing the electrons through this circuit. So at the moment, current isn't flowing. And therefore, we don't have a reading on our ammeter. Remember, an ammeter measures current flow. Let's see what happens as we increase the voltage of the battery from 0 to 0.5. Now our ammeter has a reading of 0.2 amps, and our voltage on the battery is 0.5. Remember to take this down in your table. Let's increase it even further. At 1 volt, our current is 0.4 amps, and we can see the electrons moving slightly faster. Now we're at 1.5 volts, and we have a reading of 0.6 amps. Let's increase it to 2 volts. Now we have a reading of 0.8 amps, and our electrons are moving even faster. Now if we increase it once more to 2.5 volts, our current has a reading of 1 amp. I hope you got all those values in your table. So, your results table should look a little something like this. Now, when we get results like this, we always need to plot a graph. Pause the video and plot your graph using this data. Now, when you're plotting your graph, the first thing you need to do is make sure you've got your axes correct. Then, label them with voltage and current. Next, you can add in your scales, as well as the numbers from your table, all the way from 0 to 2.5 for voltage and 0 to 1 for current. After that, plot your first point. That's at 0. The next one is at 0.2 and 0.5 on the x and y axis respectively. Then at 0.5 amps and 1 volt. Next, 0.6 and 1.5 volts. Then 0.8 and 2 volts and 1 and 2.5 volts. Afterwards, make sure you draw your line of best fit and make sure it goes through the origin. So, when you look at your graph, what sort of trend do you see? You should notice that as current increases, our voltage increases too. This means that the two are proportional. Also, what happened to voltage when current doubled? Take a look at the numbers and see if you can figure it out. What you should notice is that when current doubles, voltage also doubles. This means that the two quantities are directly proportional. This is known as Ohm's law. It's a really important law that governs electricity. And Ohm's law states that the voltage across a conductor is directly proportional to the current flowing through it. That's what we saw earlier, provided that the physical conditions such as temperature remain constant. That's it for this lesson. I hope it's been useful. If you have any questions, please ask.